Hello, welcome to Ogo Reviews. In this video, we're going to be looking at how to draw the bolt and chair conformation of cyclohexane and how to predict the stability of molecules that are in ring structures. So let's get into it. Let's look at the structure of cyclohexane. Cyclohexane is a 6-carbon ring structure. Each one of the carbons in the structure has 2 hydrogens. But because the carbons are kind of arranged in a ring, the tetrahedral structure of each carbon presents some kind of what we call ring strain. The only way to release this strain when you put all the 6 carbons in a ring is for the structure to adopt what we call a chair conformation or a bolt conformation. So we're going to take a look at what each one of these means. So looking at the structure as you have in a model kit, you can clearly see that the cyclohexane structure can be put into what we call a chair conformation. So imagine like a beach chair, right? So a beach chair has something that looks like that. So you have the end where you put your foot, and then you have the end where you kind of lay. The same way you can have the structure of cyclohexane assume that kind of conformation. And if it does, this is how it looks like. It looks like this in a sort of a 2D representation. But then if you look at the model kit, as you can see, you have some part of the cyclohexane going up and some part of it going down. Other areas going up and some areas going down. And the areas that are going up can easily be seen with different color codes, and we're going to represent our hydrogens by that. So again, each point on this cyclohexane has 2 hydrogens, okay? And some of them are pointing up, others are pointing down, and others are pointing sideways, as you can see in the model kit. And I've color coded them so that you will see the difference. We're going to talk about the different types of hydrogens we have on this particular ring shortly. So this is what we call the chair conformation. All right. Now, how do you draw this on a paper? I'm just going to teach you a little trick on how to draw the conformation on paper. So when you want to draw the chair conformation as a starter, what you do is you draw a V, and the V has to be wide as possible. So this is a wide V that is facing up. And what you do is that you kind of draw an imaginary line, and it could be in your mind, just you can gauge it, right? And then the next thing you do is that you draw a line coming down at about 60 degrees and as close as possible to this imaginary line. And then you draw that line right there. The next thing you do is that you create another imaginary line that is coming down from the end of the V on the left. So what you do is now you draw another line that moves up, but then as close as possible to the imaginary line that you just drew, and then you leave it like that. The next thing you do is that now you've created a new V right down here. So you draw another imaginary horizontal line that goes all the way across like that. And what you're going to do is that you're now going to pick a line from the top here at about 60 degrees down. And you come all the way till you kind of meet that imaginary line you have at the bottom, and you let it go. And then the next thing you do is that you connect these 2 lines. Again, these are all imaginary lines, and you don't have to draw those. It's just to guide you, all right? So again, I'm going to draw it without the imaginary lines. So I have my V shaped. This one goes about 60 degrees. And then you go up. So you get to the imaginary line right there. Now you have another imaginary line here. You don't really draw it. So you come down till you meet that particular imaginary line at about 60 degrees. And then you connect these two lines. So that's how you're going to draw your chair conformation. The same way you can flip this structure, as you can see in the model kit. If you flip it, this end will come down and that end will go up. So this happens interchangeably as the cyclohexane conformation. So you have conformer A, which can flip to conformer B, and let's see how conformer B is going to look like. So if you go to conformer B, again, you draw a V, but the V is now going to face down as wide as possible. And remember that we drew a line coming down. This time we're going to draw the line going up. So imaginary line growing up, and you make sure that this line doesn't touch it. And you draw another imaginary line here. So you come down like that. Again, this is too close to that imaginary line, so I'm going to reduce it. So let me try one more time. So you go up. And then you come down. You don't touch this imaginary line. And what you do is, now that you have this imaginary line, you create another imaginary line right here. So what I'm going to do is I'm going to move up till I sort of meet that imaginary line. And I'm going to let it go, and then I can connect these two just like that. Now, you can see that the ends have flipped, right? So we have your conformer B. So as you can see, this is just a flip. And depending on what groups you have on the structure, you'll be able to tell which one is more stable or not. Draw the chair conformation of the following compounds. Let's begin with compound number 1. Compound number 1 has a chloro and methyl group, both of them facing up. And this can be seen by the fact that we have a wedge on the substituents. So let's see how these groups are going to arrange on a chair conformation. So let's begin by drawing a chair conformation of the cyclohexane. Again, you draw a wide V, and then you go a little bit away, and then you complete your chair conformation like that. So the next thing you do is you try and number the substituents. So number 1, 2, and 3. The same way, when you draw the chair conformation, you number the carbons as well. So looking at carbon number 1, there is a axial substitution and an equatorial. And then at position number 3, there's an axial and there's an equatorial. So let's try and place these groups on these substituents. We do have carbon number 1, the chloro group is facing up, which is the axial position. And then the equatorial is definitely going to be a hydrogen. At position number 3, we have methyl group facing up, so we're going to put a methyl group at the up position. And that, of course, is going to be another axial. And the hydrogen will be equatorial. Right? Now, is this the only way to represent the structure? No. We can actually have what we call a ring flip. What happens in ring flipping is that these carbons at the ends of the chair tend to kind of flip. So this goes down and that goes up. So let's see how that looks in terms of the structure. So you have this. Correct. So now we do have your carbon number 1 here, and that's going to be carbon number 4 there, and this is going to be carbon number 3. So all that is happening is that, again, you're going to have equatorial and axial. Carbon number 3, you're going to have axial, equatorial. So what we expect is that anything that is in the axial position before the flip becomes equatorial. So we know that the chloro was in the axial position, so it's going to be the one occupying the equatorial position on carbon number 1. The hydrogen, which was in the equatorial, becomes axial. So that is the deal. If you want to flip the structure, anything that is axial becomes equatorial. Carbon number 3 we have the methyl group in the equatorial position and the hydrogen in axial position. Now, which of these two ring structures, is A or B, is more stable? The correct answer is B is going to be more stable than A. The reason is, in A, there's a lot of interaction between these axial groups. So there's going to be a lot of interaction, fighting going on at the top. Whereas these in ring B, the groups are kind of far away from each other and there is not much interaction going on. Both of them are in the equatorial position. So equatorial position is more preferable when you have groups in the cyclohexane structure or any kind of ring structure thereof. So this is going to be more stable than that one. With number 2, same thing can be used. We have numbering of the carbons. So we have 1 and 4. So what we're going to do is that we're going to use the same way. So this is carbon number 1, that's going to be carbon number 4. At carbon number 1, we're going to have equatorial, axial. Carbon number 4, we are going to have axial, equatorial. So you can see at carbon number 1, the bromo group is facing up. So that's going to be in equatorial position. And the hydrogen is going to be pointing down. What about carbon number 4? Yes, the ethyl group is facing down. The hydrogen is going to face up. So this is going to be one conformation. Again, if you flipped it, what you expect is that this is going to go up and that is going to come down. So let's see how that goes. So you're going to have something that looks like this. You have your carbon number 4 facing down and carbon number 1 facing up. So at 1 you have axial equatorial, at 4 you have axial equatorial. Again, you can clean this up, but I'm just doing it in a hurried way. So 4, you do have ethyl group that is facing down. So you're going to put ethyl group here. And at the other end, you're going to have the bromo group facing up. And that is going to be in the axial position at this point. So these two groups, of course, you can predict that this is going to be a more stable conformation than that, because the ethyl group and the bromo group are in equatorial position, and that is a more preferable way for the groups to occupy compared to in the axial position. Let's look at example 3. Same kind of scenario. Again, that is a very horrible way to represent this, but let's try and clean it up a little bit. So you have this, that, there we go. We have the hydroxy group facing up, and then at position 2, you have the methyl group facing down. So you have your hydrogens facing like that. And again, you can clean your structure up. If you flip this, meaning this goes up, that comes down, you're going to have something that looks like this. And again, this is going to be your hydroxy group, which is facing up right here, and your hydrogen facing down. And of course, you're going to have your hydrogen facing up and your methyl group facing down and in equatorial position. So you can quite see that this is going to be more unstable compared to that. So this is going to be a more stable form, and therefore the forward reaction is, the forward conversion is more favored.